We've said that work is the integral of P dV, but it depends on the path we've taken. It depends on the process we use to go from one state to another. So we're going to be looking at work for various processes. And the first process we're going to consider is a process where pressure is constant. So considering this constant pressure process, which we could show on a PV plot, we go from state 1 to state 2 where the pressure remains constant. So we've got the same pressure at states 1 and 2. At state 1 we've got volume V1, and at state 2 we've got volume V2. We said that del W is equal to P dV, and we could say the work in going from state 1 to state 2 is the integral of P dV, or it's the area under the process on a PV plot. Now, intuitively, you could say, well, that's a rectangle, it's just base times height, but we're going to go ahead and work this integral. Because the pressure is constant, we can pull it through the integral, and we can say that the work is P times dV evaluated from state 1 to state 2, or the work is equal to P times the integral of dV, which is V, evaluated from V2 to V1, or we get that it's P times V2 minus V1. So the work for our process where pressure is constant is pressure times the quantity V2 minus V1. You'll see that equation on equation sheet for exam 2, and you just need to know which processes to use that work for. We'll consider a second process where the product of P times V is equal to a constant. So once again, let's consider a process where P times V is equal to a constant. So if we were to plot that process on a PV plot, we've got state 1, and we've got state 2, and we've got a process where P times V is constant. At state 1, we've got P1 and V1. At state 2, we've got P2 and V2. If we have a process where P times V is constant, then P1 times V1 will equal P2 times V2. But more importantly, for any process for any state along this process, if I take the product of P and V, it will be the same value. Now the work in going from state 1 to state 2 is equal to the integral of P dV evaluated from state 1 to state 2, or we could say that's the area under the process, or the area under the curve. Now I'm integrating with respect to V, but P is changing also. So I can use that P times V equals a constant to get pressure as a function of volume. So I get that P is a constant over V. So the work is the integral of a constant over dV, a constant over V dV. The constant can be pulled through the integral, so I get work as a constant times the integral of dV over V evaluated from state 1 to state 2. And that's just a constant times the natural log of V, where natural log of V is the integral of dV over V. And we'd evaluate that from state 1 to state 2, or from V1 to V2. So I get a constant times the quantity natural log of V2 minus natural log of V1. And if we remember that logs are exponents, we get that it's a constant times the natural log of V2 over V1. So you'd say, okay, well, what's the constant? Well, remember, that constant is just P1 times V1, or you could say P2 times V2. So the work in going from state 1 to state 2 is equal to P1 V1 times the natural log of V2 over V1 for a process where P times V is equal to a constant. There are lots of different things you can do algebraically, and so you can use P2 V2, and looking at P1 V1 equal to P2 V2, you could also take that natural log as a natural log of V1 over V2, but that's just fun with algebra. Looking at another process, we can have a process where P times V to the n is equal to a constant. Only V is raised to the power n, and in this case n will not equal 1. We just looked at that in the previous example. We call these types of processes a polytropic process. So if we're looking at this polytropic process where P times V to the n is equal to a constant and n is not equal to 1, looking at the process on the PV plot, we can go from state 1 to state 2 in a process where P times V to the n is equal to a constant. And you'll say, well, that looks exactly the same, but it's not. But in this process, P1 times V1 to the n will be equal to P2 times V2 to the n. But as I said in the previous example, more importantly, if I go along this curve, anywhere along that process, if I take the product of P and V to the n, they will equal the same value. Now, I said this looked like the other curve. Well, it looks like it, but I've put the equation down, which is P times V to the n is equal to a constant. So it's telling you what that curve is. We know that the work is the integral of P dV, so it's the area under the process. And using P times V to the n is equal to a constant, we can say that P is a constant divided by V to the n. So we can say that work is the constant times the integral of V to the minus n dV. Remember, 1 over V to the n is just V to the minus n. Evaluating this integral, I get that I have a constant times V to the minus n plus 1 over minus n plus 1. You've done this many times before, and we'll evaluate that from V1 to V2. I don't like the minus sign hanging out in front of the n, so I'm just going to use the property that addition is commutative. So instead of minus n plus 1, I'm just going to say n minus 1. So we get that the work is equal to a constant times V2 to the 1 minus n minus a constant times V1 to the 1 minus n, all over 1 minus n. And you'd say, what should that constant be? Well, going back up to the top here, I'm thinking I could use P1 V1 to the n or P2 V2 to the n. And we're looking at what's convenient. We could say it's P2 V2 to the n. That would be my constant, times V2 to the 1 minus n. And then I'd subtract from that. The second time I look at the constant, I'll just call it P1 V1 to the n times V1 to the 1 minus n. All of that would be over 1 minus n. Simplifying, I get that the work from state 1 to state 2 is P2 V2 minus P1 V1 over 1 minus n. That's the equation that you would use for processes where P times V to the n is equal to a constant and n is not equal to 1. You will see this work equation also on the equation sheet for exam 2. Now finally we can look at work and processes involving linear springs. Linear springs are springs where the spring constant is linear. There's a linear relationship between force and displacement. But more importantly for you in thermodynamics, if I'm going from state 1 to state 2 on a PV plot and the piston is spring-loaded and that spring is a linear spring, I will connect the two states with a straight line. The work in going from state 1 to state 2, we've already established, is the area under the process on a PV plot. That is the work. You'll say, okay, well, how do I do that? The easy way is the work is the area under the process, so we could say that the work is the triangle plus the rectangle, where the area of the triangle is 1/2 the base, which is V2 minus V1, times the height, which is P2 minus P1. Once again, looking at the triangle, we have the base is V2 minus V1, and the height is P2 minus P1. And then we'll add to that the area of the rectangle, which has a base of V2 minus V1 and a height of P1. Going ahead and distributing the 1/2 on the pressures and then adding the two terms together, we end up with an equation that is the equation for a trapezoid, which is the work would be equal to 1/2 the base, which is V2 minus V1, times the two heights. The heights of that trapezoid would be P2 and P1. So we get that the equation for a process when you've got a linear spring would be equal to 1/2 V2 minus V1 times P2 plus P1. This equation is not on the equation sheet for exam 2, but that's okay because you know it's the area of the rectangle plus the area of the triangle. Now, you could do it another way, which is you could get the equation of the line, where the equation of the line is y is equal to mx plus b, or you could say pressure is equal to m times volume plus b, where the slope, m, is equal to P2 minus P1 over V2 minus V1, and then you could get the intercept B, which is equal to P1 times V2 minus P2 times V1 over V2 minus V1, and integrate. But I think we can all agree that it's just easier to add the area of the rectangle and the area of the triangle.